And so last time some things didn't show up properly when we were doing our Python session. So I decided to record a small video for you all again, so that we can have a better understanding how we can do history matching for our pressure transient data, and how we can get some results from our pressure transient analysis, right? So we will start briefly by reviewing our Python script. So we will import different libraries that will be required for our computations, such as math, which can be used for mathematical operations, pandas. Here specifically, I'm using it for simply importing our Excel files, numpy, which can be used for array operations. Matplotlib is primarily used for visualization purposes, such as plotting of our functions, right? SciPy is quite popular library nowadays due to the data science and things like that, and we will be using nonlinear regression algorithms through the curve fit functions that we are importing from SciPy library, right? And as well as we can also use our modified Bessel functions from SciPy library. So what we have to do next, we have to input our pressure transient data, right? Which includes the information about our test. And this information is not quite important for us right now because we have simply infinite acting reservoir flow included in this script, right? And what we have here is our production time prior to shut-in, flow rate prior to shut-in, right? We have to also include our fluid properties, such as formation volume factor, total compressibility, oil viscosity. Reservoir and well properties also needs to be included, which are reservoir thickness, porosity, wellbore radius. And the next step is going to be to read our build-up test data. And here I'm reading it from Excel file. And this Excel has the information about our shut-in time, as well as our pressure difference, right? Delta P we're going to use. And yeah, we have to extract the appropriate data from our Excel tables to our delta T and delta P options. And later we have to convert and do some sort of time corrections, because the production time that we have here is quite small. So we have to account for that. We cannot just use our delta T right away. And why is it so? It's the good description is given in Agarwal paper. If somebody is interested, you can just email me and I can explain it to you with other details. And so after our input, what we need to do is to compute our pressure derivative function, right? And we are using here simple Burdett pressure derivative, which includes some sort of smoothing parameter. And the rule of thumb, and that's how it's working in commercial software, is that by default, they have a factor of either 0.1 or 0.2. So they already smooth the data for you. Let's see if we don't really smooth any data. Let's run our model and let's see our input. And so, by the way, that's what I'm showing here, right? I'm showing our simple Cartesian plot, right? Where we have a pressure drop function versus shut-in time. I'm showing here our log-log plot, right? Which is going to be the primary our interest. So we have here our pressure drop data and pressure drop derivative, right? So as you can see, this derivative is a little bit noisy. The data for this derivative is noisy, so we'll need to smooth it eventually. And what else I'm plotting here is our Horner time, as well as Agarwal effective time, the ones that I showed it in our Python script, right? And as well as I'm plotting here pressure drop derivative on this semi-log plot. But it's not going to be very like useful, to be honest, but it's okay. Okay, so as you can see, the data here is a little bit noisy for our pressure drop derivative. So let's smooth it a little bit. Let's use, okay, let's not do that. Let's do 0.2, right? Let's see how we can smooth our data. So you see right now it's looks much better. So we can essentially use this data in order to do our next matching. And let's try to do like something crazy, 0.5, for example. So you see, you start to see this kind of like wiggles here. So we don't really want, as well as you start failing at the wellbore storage part, right? Your derivative starts to deviate from the slope of equal to 1. So you don't really want to over smooth your data. So let's just stick with this coefficient of 0.2, right? Let's just run one more time. Make sure that everything works correctly. Okay, looks good. Okay, so since we computed our pressure derivative, it looks reasonable. We can do optimization and try to history match our data, right? So what we are using here is some sort of nonlinear regression technique. It's called Levenberg-Marquardt. I don't really know how it works behind the thing, but it definitely is doing a good job on optimization of a problem. And apparently this problem is not as complex as the ones that you may have during your history matching in reservoir simulation problems, right? Because you have much more constraints, right? You have much more unknowns. But here, what we are using is essentially permeability, skin factor, and wellbore storage. So those are going to be 3 of our unknowns, right? And we have to specify our initial estimate, lower bound, and upper bound, right? So in this case, we are specifying, well, let's do something like that, right? Let's assume that our lower bound of permeability is 20 millidar-C. Our initial estimate is like, let's put it like 25, and upper bound is 30, right? And let's try to specify our skin factor, I don't know, like just 5, 1, and like 10. Since we didn't try to optimize yet, it's very hard to predict what we're gonna have, but apparently, based on the data we saw, we have some skin factor due to the significant hump there, and we have some wellbore storage coefficient, and I'll just stick with those parameters here. And so what we're trying to do, we will try to compute our analytical model for pressure as well as pressure derivative, and try to compare it with our delta P and delta P prime. And so let's go to find parameters function. So as you see, these are our 3 functions that we don't know: permeability, skin factor, and wellbore storage coefficient. So what we have to do next, we have to convert our variables into dimensionless units, such as dimensionless time, as well as dimensionless wellbore store coefficient. And yeah, after we did that, we have to, we'll start with our analytical pressure and pressure derivative calculations. So we have to call our Gower and Stackfast algorithm. And as was discussed previously, this algorithm can be used in order to invert your solution from Laplace space to real space. And this is the very important coefficient that I call here L, but during presentation, apparently I showed it as N. Let's see, what does it mean? Where it is? Okay, here we go. So as you can see, this is N that I was talking about, right? And so we have to optimize for our number of terms in Gauer approximation. So in our particular code, I have it as 12, and I'm quite sure it's working fine, but it's a good number for this specific problem. For each specific problem, this number is gonna vary, right? So you may think that the increase of terms in Gauer approximation will lead to a better solution, but this is not the case, because as you can see here, we are converging to our exact solution, but suddenly we have a divergence of our solution when n is equal to 18, right? So it's not matching our exact solution. So we have to be very careful with that, right? For now, let's stick with simply 12, right? And let me show you. Okay, no, I'll show you a little bit later. And so this is Gauer Stackfast algorithm mentioned before. And here we have our problem, right? Our solution in Laplace space, in Laplace domain. And as you can see here, we have our modified Bessel functions, right? And that's where all the theory that was discussed previously is being used, right? So we have our modified Bessel function of second kind of zero order and of first order, right? And this solution is slightly modified modified from the ones that we derived during the webinar, because it also includes the skin factor and Wellbore storage coefficient. And as you can see here, I'm using dimensionless Wellbore storage. Right, so so it's very easy also to compute our pressure derivative, right? We have to just multiply our Laplace coefficient by our function. And that's just by definition, if you look it up on the properties of Laplace derivatives in Laplace space. And so, yes. So after we computed results from our Gauer Stackfast algorithm, here I have like solution matrix, right? And this corresponds to our pressure data, and this corresponds to our pressure derivative, right? So we will have to also convert our results from dimensionless form to dimensional, right? By just using those simple coefficients, as you can see here. And we are returning our pressure data as well as our pressure derivative. And now we're going to optimize it, and like it's going to optimize and find the appropriate solution. So let's try to run it and see what kind of match we are getting, and if we need to specify other parameters there. Okay, so let's look at the model here. So as you can see, we are not getting a good match right now. So what we have to do is essentially to decrease our permeability, right? And that's, let me show you. Here, right? So based on this chart, we can conclude that, okay, let me do it in 2 screens. As you can see here, what we need to do is to decrease our permeability, right? We want to have our derivative going upwards in order to match our data. And so let's change the bounds that we have in our system. Let's change it, for example, to 10. Oops. Let's run and let's see what's going to happen. And so now, as you can see, we are getting pretty good match right here. So we matched our wellbore storage region. We get a proper match for our hump, which corresponds to some skin value that we'll read now, as well as we start seeing our infinite infinite acting radial flow right at the end of this portion. And we matched pretty much all the data on different type of plotting functions that we are using. And as you can see on the right bottom, this is the match that we are getting. Essentially, permeability is 1224 millidarcy. This is our wellbore storage coefficients that we are having, as well as quite high skin factor, 9.4. So this is how you can make your analysis, right? I just oversimplified it a little bit because it would be much harder to show some more complex problem, but anyway. And let's see if we increase the number of terms in Gauss-Stackfast algorithm. What's gonna happen if you have like 20 of those? I just want to see you how it will diverge. You see, we are not getting like proper result, first of all, but let's increase even more. I just want to see you it failing, completely failing. Yeah, you see, this is the effect that it's doing. So you have to be very careful while optimizing for that number, right? For number of terms in Gauss-Stackfast algorithm, because that will define if your solution is correct or wrong. And this number in commercial software is essentially used by default, so you cannot change it. And yeah, so let's leave it as 12. And you see we're getting pretty good match, essentially. And so this, this green line is essentially our pressure drop beta derivative, right? And if to put it simply, it's just our pressure drop derivative divided by our pressure drop, right? And you can also do some sort of additional diagnostics with it, but yeah, that's how you can use it. And yes, and that's it. I think that's it. Okay, thank you for your attention one more time.